Alright, today's lecture is on quadric surfaces. Quadric surfaces are shapes in the R3 space that are kind of a generalization of conic sections that you might find in R2. We'll go through these kind of carefully. Let's start with looking at some of the graphs that we're already aware of how to draw. So we've already learned about spheres, which have equations like this. We've learned about planes, which have equations like this. There should probably be there's a J here if it is not centered at the origin. So you could put a J in place of the 0. You can move this point away from the origin in the planes. Same thing with the sphere. You can adjust where it's located and things like that. But anyway, essentially we have these two equations here, one for spheres, one for planes, and we spent a little bit of time understanding those. We also talked about lines, but here we're going to talk about surfaces a little bit more. The most simplest kind of surface after spheres and planes that you can talk about is the notion of what's called a cylinder. This is a surface that consists of a whole bunch of lines that are parallel to a given axis and pass through a given curve in the plane. Now that sounds a little funny, but so I think the better way to think of it is you take a curve that's in the XY plane or whatever plane that you want to have, and you stack copies of this curve down a line. A picture of such a thing is this parabolic cylinder here. So if I look, I've got that this parabolic cylinder is basically a stacking of a bunch of these parabolas that are just stacked along these lines here. The parabolas that are being stacked are called traces, and the lines here that the parabolas are being stacked through are called rulings. And that's what makes a cylinder. So a cylinder is essentially a graph that has been stacked through a bunch of lines. Okay. By the way, this function here, if you look, the parabola for this equation is parallel to the xz plane, and the y-coordinate is kind of the ruling part. So the equation for this plane would be z is equal to x squared. And that would actually describe everything because the y value doesn't matter. And so now for any y value you pick, you have to graph the parabola z equals x squared. And that's why those parabolas get stacked through all the different possible y values. Perhaps a more familiar cylinder we have is one where the shape that's being stacked are circles. All right. Now if you look here, each of these circles that are being stacked are parallel to the zy plane. So this would, and they have a radius of 2, so this would be z squared plus y squared is equal to 4. And the x coordinate, you notice, doesn't make any difference, and so that's why you get the stacking through lines that are parallel to the x-axis. So for every x value, you get another one of these circles here, and that's what creates the cylinder. So essentially, you know you're going to have a cylinder basically whenever you have an equation for your graph that looks like a regular equation in just two coordinates, but the third coordinate's not present. Now, of course, you could have cylinders that actually point in any kind of line, in which case you may get some x, y, and z dependence and still have a cylinder. But most of the time, we'll give you examples that are a little bit easier, like this. Now, the next type of surface we might be able to, that we're going to talk about is the idea of these quadric surfaces. And what this does is a quadric surface is any surface whose equation looks like this general quadratic equation. So if you notice, this is all the possible ways I can make a second degree polynomial. I have x squared, y squared, z squared, and then I have products of each one of them. Those are also degree 2 kinds of things. And then I've got the linear pieces and the constant pieces. So you can see that that's essentially what this is just the most general possible multivariate degree 2 polynomial. Quadric surface is anything that has such a graph. Well, fortunately, we don't have to mess with that kind of beast. It turns out that with that graph, you can rotate it and translate that equation to get one of these two forms down here. Now, specifically, these equations are translated so that they're centered at the origin and rotated so that they're symmetric about the z-axis. But you could take these equations here and rotate them or translate them how you want to get what you need to. For example, if I wanted, you notice I've got a z that's linear here with some x squareds and y squareds over here. If I wanted this equation to be symmetric to, say, the y-axis, I'd use x squared and z squared, but I'd make this guy just by. All right. So whoever basically is the degree 1 term is the one where the symmetry is. All right, so let's take a look at a few examples of these quadric surfaces. The first one is an ellipsoid. And it has an equation that looks like this. You'll notice you get x squareds plus y squared plus z squareds. If the a, b, and c are all the same, then this is just a sphere. Because they're all positive, it turns out that all the traces, whichever way you want, whether it's this way, or it's this way, or if you want even this way, all the possible traces that you could draw turn out to be ellipses. Another type is an elliptic paraboloid. This is where you have your x squared plus y squared part here, and it's equal to a linear term z. Now, if you look at this, what essentially this means is that for every z equals constant, you're going to get a trace that's an ellipse. Okay, and that's exactly what you're seeing here. These ellipses that are being drawn are exactly the equations where z is a constant and you get an ellipse out. Okay, so whichever variable is raised to the first power, by the way, is where the axis of the paraboloid is. So if I had a y squared and a z squared on this side over here, and on the other side I had an x, then I'd get an elliptic paraboloid that opens up into the x-axis. Another type is a hyperbolic paraboloid, which looks exactly the same as before, only it has a minus sign over here instead of a plus sign. And all this does is changes the horizontal traces to be hyperbolas now instead of parabolas. Instead of ellipses. The vertical traces are still parabolas, though. The case that we have here is where c is less than 0. And it looks a little bit different if c is greater than 0, but essentially you can see that it's drawing sort of like a saddle point. Okay? You can also get cones, and that's where you have your x squared plus y squared over here is equal to z squared over c squared. So this is similar to the elliptic paraboloid, only now the z is squared as well. In this case, the horizontal traces this way are ellipses, but the vertical traces this way are hyperbolas. And that's hence the cone shape that you get. So, and the cone contains both the top and the bottom pieces. By the way, if you notice when if you do a very specific trace that goes through the point, that trace, instead of being a hyperbola, is just a pair of lines. Another type of quadric surface is a hyperboloid. And in this case, this actually looks exactly like the equation for a cone, except that you get this 1 out here. Now, when I wrote the cone before, I had an equal sign sort of in this position. So if you just add that or subtract that to the other side, you would have had a 0 here if it was a hyperboloid, if it were a cone. The 1 here is what forces it to sort of come out a little bit from the origin, and that's why you get a hyperboloid. The 1 sheet just refers to the fact that there's only one surface here that's attached. So you can see that the horizontal traces are still ellipses and the vertical traces are hyperbolas. So it has a lot of the same properties that cones have, it's just that it doesn't pinch off at a point in the middle. A hyperboloid of 2 sheets is exactly the same thing, except you notice on the left-hand side the signs are reversed from before. Still equals 1 though. This is called 2 sheets because it ends up deleting sort of the inside, and you end up with 2 different distinct pieces of the graph. All right, and it's the 2 minus signs that actually give away the fact that this is a hyperboloid of 2 sheets. Now let's do some examples then. So let's take a look first at a surface that's described by this equation, and let's see if we can figure out what it looks like. First off, we notice that it looks like just a z and a y equation. So if I wanted to, I could draw this in a ZY plane. And what I draw is a parabola. Notice I'm kind of treating the y as the independent variable. This would end up being a parabola that opens down because of the negative, and then is shifted up one. So it would look like that kind of a graph. All right. However, there's no x dependence here. So every single time I move along x, I'm going to get exactly a copy of that. So if I come over here and draw my XYZ space, X, Y, Z, every x value is going to produce the same parabola. And what I end up getting is a parabolic cylinder. Okay, so you can see the parabolic shape in it, where all the different traces are parabolas, but as I moved along the x values, all I did was stack those parabolas together. And that's what I'd get out of a graph like this, and it's because the x coordinates sort of didn't matter. So the description is that it's a parabolic cylinder whose vertex is along the line z, plane z equals 1. So if you want, there's a vertex at 0, 0, 1 for one of the spaces. All right, so let's do another one. Let's take a look at a quadric surface like this. We recognize real fast that it's a quadric surface of at the very least, because it has quadratic portions. It's basically a general quadratic equation. But in order to understand which one, we sort of have to we need to translate it into one of those ones that we had drawn a picture of. And in order to do that, you'll notice it might be helpful to complete the squares here. So that's the first thing we're going to do, is complete the squares. So I'm going to collect the x's together. I'm going to collect the y's together and leave the other guys outside, and leave some spaces here and here and here so that I can add in and take out things to make the completing the square process work. So to complete the square, I look at the middle term here. I divide the coefficient in half, so I take -2 divided in half, which would be -1. I add the 1 into this position here, and then subtract it out here to keep it balanced. And then I do the same process here. So -6 divided by 2 is -3, squared is 9, so I'm going to add 9 to the other side, or subtract 9 on the outside. So here you have it. You got your +1, your +9. Well, here you have your -1 and your -9 in order to keep everything balanced. Now it's pretty cool. These guys right here cancel each other, so they're just gone. These guys factor as perfect square trinomials, and you end up with something that looks like this. You can add the z to the other side, and you land at an equation like this here. Now, if we wanted to figure out what this looks like, if you notice that for every z equals constant, so you pick a number for z, this will produce a circle in the xy, parallel to the xy plane, that's centered at 1, 3 in the xy plane, and has a radius equal to the square root of whatever constant you picked for z to be. So essentially what this is for every z value, you're getting a trace of a circle here. And as z gets bigger, as it goes up, it's going to get larger and larger. Also notice, because we're adding squares here, this forces that z can't be negative. So for any negative value of z, you don't get a trace at all. This will create what we call a circular paraboloid. So what you get, draw it, x, here's y, here's z, and at z equals 0, you get, this is equal to 0, all you get is a single point, xy, that's listed at 1 in the x and 1, 2, 3 in the y. So it starts right here in the xy plane. There's a point, And then as we get larger, if we go up to z equals 1, we're going to get a circle of radius 1 about that. And we go up to 2, we'll get a circle of radius square root of 2. So essentially what we get what we get out of this is we get a parabola that kind of moves like this. So boy, that looks terrible. I can maybe smooth this out a little bit. So you get essentially a parabola that's opening up, and the axis it's going on is this sort of 1, 3, and then your z coordinate, whichever one you're going to pick, that's the axis that you're using. And the parabola is just opening up, and for each z equals constant, you get a trace of a circle centered at 1, 3 of radius square root of z. And so that's the surface you get. So basically the idea here is whenever you're given an equation like this that you recognize it's a quadric surface, you may need to complete the square a little bit in order to get it to something that you can recognize. Then you go through that list of 6 different things, you figure out which one it draws, and then draw it accordingly. So as you get a little bit better at this, you'll start memorizing those six graphs, and you'll be able to do this right off the fly. It's kind of similar to the list of equations and graphs that you already know from in the xy plane. Like you know what x squared looks like. So if I give you a quadratic that's been shifted around, you can still draw that. It's the same exact idea. It's just now we have a larger array of parent functions that we can use. And we just need to be able to identify them. Well, hopefully you found this section enlightening. We are pretty much finished there. So I can't leave without a cat joke. So here I have a cat trapped in a cone, trapped in a conic section. And you know, even cats basically get trapped in math sometimes. So anyway, hopefully this helps you out with some of your homework. And I'll be back on Monday so you guys can ask questions.